In section 9.4, we're going to take a look at two comparison tests. One is comparing the actual series and the other is comparing limits. For the first test, the direct comparison test, we're going to take a look at a series that doesn't fit any of our rules so far, but is really stinking close. And so what we can do is we can do a direct comparison between a series that we can easily determine converges or diverges and compare it to one that almost fits that pattern but not quite. Again, as we continue through chapter 9, it's very important that you keep track of what you know. Here are my notes for keeping track of which test we've learned, when to use them, and the conclusion for each. You should be writing your own notes. Obviously, I have not left myself a lot of room, but you could have a whole page where you just write examples and anything else that you need, because this does get a little overwhelming trying to remember all of the tests that we know. The direct comparison test is a great test that allows us to determine convergence or divergence of a series that maybe isn't so easy to determine convergence or divergence for directly. So what we can do instead is find a series that is similar to it that we can find convergence or divergence for based on one of the tests that we've already learned, the p-series test, the integral test, the nth term test, etc. If we can determine convergence or divergence of a similar series, then we can do a comparison. And here's how we do it. We need for this to be true, which is that a sub n is less than or equal to b sub n, and they both have to be non-negative. So that's the first thing we need to do. The second thing we need to do is to then say one of these two things. So this is step 2. Either that b sub n converges and therefore a sub n converges, or that a sub n diverges, then b sub n diverges. And then we can, so that's 2, and then 3, of course, is to say the second part of that. So we have to show that one of them converges or diverges, and therefore the other converges or diverges. So here's our strategy. Our strategy, so I guess step 0, is to make a guess. I want to make a guess as to whether or not my function converges or diverges. Now on this one it's pretty easy to do because I've already given you a function to compare it to, and I've already told you that that function converges. Okay, but clearly that's not going to be the case most of the time. So my guess is going to be, again, that this is going to be a convergent series. So that's my guess. And here's why you need to make a guess. Because if you have a guess where you think it converges, so if you think your function is going to converge, then that means we need to assign our value, or our series is going to be the a sub n. And then we're going to need to find some b sub n that is greater. So our series is a sub n, we have to find a b sub n to compare. If our guess is that it diverges, that's using this one, then I need to let our series, the one that we're trying to determine, be b sub n, and then I need to find a divergent a sub n. So that's our strategy. So again, this one's going to be pretty straightforward because I've already given you exactly what you need to do. I've given you the series to compare it to. But let's go ahead and work through it anyway. So I made my guess, and my guess is that it's going to converge. So I'm going to go with this strategy. So I'm going to let a sub n be 1 over n cubed plus 1, and b sub n is going to then be 1 over n cubed. And so I have to then show that a sub n, which is 1 over n cubed plus 1, is less than or equal to 1 over n cubed. Now I can do this a couple of different ways. I can just look at this analytically and say, okay, if I'm adding 1 to my denominator, then my denominator is bigger, which means the overall number is smaller, and therefore this is true. So again, I don't have to really show anything. I can just say, so this is true. Great. So that's true, and I can move on. Now, if I'm not sure, remember you can always go term by term comparison. I can plug in 1 and say, okay, if I'm plugging in 1 for n, that's going to be 1 over 1 cubed plus 1, or 1 over 2. If I'm plugging in 2, that's 1 over 2 cubed plus 1, that's 1/9. And if I plug in 3, that's 1 over 28. And then I could look at the same for this series and say 1 over 1 cubed is 1, 1 over 2 cubed is 1/8, 1 over 3 cubed is 1/27, and hopefully I can see that 1 is greater than 1/2, and 1/8 is greater than 1/9, and 1/27 is greater than 1/28. And so again, whichever way you do it, I've now said that that is true, that this in fact is true, that a sub n is less than or equal to b sub n. My second step is to then show that my b sub n, in this case, converges. Well, I already did that up here in my directions. I said the summation as n goes from 1 to infinity of 1 over n cubed is a convergent p-series with p is equal to 3, which is greater than 1. And then the last step would then to say, therefore, the summation as n goes from 1 to infinity of 1 over n cubed plus 1 converges by comparison to my convergent p-series of the summation as n goes from 1 to infinity of 1 over n cubed. So that's really all three parts. Step 1, show that the inequality is true. Step 2, show that the one that we know about either converges or diverges depending on your situation. And step 3, say therefore by comparison our new function converges or diverges. Let's take a look at another example. And again, I've written the rules up there for you, but the easy way to remember it is that if our guess is that it converges, then we make our series that we're trying to find a sub n, and if we think it diverges, then we make it b sub n. So the way that I remember it is C, which is first in the alphabet before D, goes with A, which is first in the alphabet before B. So the two that are first, C and A, go together, and the two that are second, D and B, go together. So let's take a look at this question. And in this question, I'm looking at the function 1 over 2 plus 3 times n squared. So just thinking about what I think is going to happen, and again, feel free to take out a calculator and graph it, but I don't want you to rely too much on graphing because I really want you to be able to think through this. If I think through this, remember this value is going to get bigger and bigger and bigger and bigger and bigger, and really that's the most influential term. So I'm going to have 1 over a very large value, and so my guess is that I'm going to take 1 divided by a very large value, and this is going to converge to 0. So that's my guess. My guess is convergent. So if it's convergent, I'm going to let my series be a sub n. So we're going to let a sub n be 1 over 2 plus 3n squared. And b sub n is going to be some sort of series that is similar to that I know converges. So that's the trick, is I need to find something here that I know converges by some property that I've already learned or some test that I've already learned. So what's similar to this that I know converges? Well, what if I compared this to taking this 2 out of it? What if I just compared it to 1 over 3n squared? Can I do that? Well, is that one of my tests? So if b sub n can be written, let's go ahead and first of all, sorry, I got distracted. I started moving on to step 2, and I haven't even done step 1 yet. So step 1, remember, is for us to say that a sub n is less than or equal to b sub n. So a sub n is 1 over 2 plus 3 times n squared, and b sub n is 1 over 3n squared. And is it true that a sub n is less than or equal to b sub n? And again, just like on our last example, if I'm increasing the denominator, then the overall number decreases. So yes, this is true. So I'm going to say, so that's true. That's step 1. Step 2 says, okay, now I have to, because I'm guessing convergent, again, I'm using this first one. I'm saying, let's take a look at the summation as n goes from 1 to infinity of b sub n. So that's 1 over 3n squared. And I want to be able to write that in a format that I can easily find convergence for. So I'm going to write this as 1/3. I'm bringing the 1/3 out. The summation as n goes from 1 to infinity of 1 over n squared. So what is this series? Well, just like on our last example, I've got a base that is changing and an exponent that is remaining constant. This is a p-series. So I'm going to say, oops, I'm going to not change colors. I'm going to say that the series as n equals 1 to infinity of 1 over n squared is a convergent p-series with p equal to 2, which is greater than 1. Step 3 says because I have shown 1 and 2 are correct, then I can say the second part of that statement. Therefore, the summation as n goes from 1 to infinity of 1 over 2 plus 3n squared converges by direct comparison to the convergent p-series the summation as n goes from 1 to infinity, or 1/3 times the summation as n goes from 1 to infinity of 1 over n squared. Done. Let's take a look now at another example, and this might look really similar to questions that we've done, and you might be thinking, all right, she's getting lazy, she's just giving us another convergent p-series, we've already done 2 of those. And while I am lazy enough to give you another p-series, this one is actually going to be divergent. So let's take a look at why. So again, before we get started, remember that step 0 is to make a guess. And if I guess convergent, then I'm going to let my given value be a sub n. And if I guess divergent, I'm going to let my given value be b sub n. So taking a look at my function, I have 1 over 2n minus 1. And again, you might not see right away that this is a p-series, except that I already said at the beginning it was going to be a p-series. So if I'm thinking about this, remember this is going to possibly be very similar to 1 over n, which is, if you'll recall, the harmonic p-series where p is equal to 1. Now, I know that the harmonic p-series is divergent. And so that's going to be my guess. My guess is that this guy is also going to be divergent. So that's step 0. So step 1 is to say, let b sub n be 1 over 2n minus 1. And then let a sub n, and here's where it gets tricky, I have to now come up with a function so that a sub n is less than or equal to b sub n. Or my new function has to be less than or equal to 1 over 2n minus 1. Now, if I try to use 1 over n, which is what we talked about here, which is divergent, this inequality does not hold true. 1 over n is not less than 2n minus 1. So a lot of people don't check that. They say, oh, this is a great one to compare it to. Let's move forward. But if I did some direct comparison, if I plugged in 1, I would get 1 over 1, which is 1, 1 over 2, 1 over 3 for my first series. And for my second, I would get 1 over 2 times 1 minus 1, which is 1, and then 1 over 2 times 2 minus 1, so that's 1/3, and 1/2 is greater than 1/3. So this doesn't work. So that's where it's really important that you pay attention to step 1. So instead, what if I compared it to 1 over 2n? Well, let's see if that works. And again, if you're not sure, I could just obviously very easily look at this and say, okay, well, if I'm decreasing my denominator, then my overall value is increasing, and therefore this is going to hold true. Or I could look at my term-by-term comparison once again. So I'm going to use 1 over 2n, which means then step 2 is to take a look at this function, and I'm going to show that that function diverges. So I'm using 2 that says we're going to take a look at the summation as n equals 1 to infinity of 1 over 2n. I'm going to rewrite this as 1/2 times the summation as n equals 1 to infinity of 1 over n. Well, we've already talked about this. I know that this is how do I want to write that? A sub n diverges because it is a p-series with p equals 1, remember that's n to the first, which is less than or equal to 1. And therefore I can say, again, because this is true, and because this is true, I'm going to say, therefore, the summation from 1 to infinity of b sub n, which is 1 over 2n minus 1, diverges by direct comparison. Oops, try to spell comparison right. Direct comparison to my divergent p-series, which is the summation as n goes from 1 to infinity. I had the 1/2 out here and the 1 over n in here. Let's just do one last example because I wanted to do one where we're not comparing to a convergent or divergent p-series, but in fact a different series altogether. So I'm looking at the summation as n goes from 1 to infinity of 6 to the n plus n over 5 to the n minus 1. And again, this one's not easy to do directly, so that's why we're going to use the direct comparison test. So what I want to do is think about what type of function does this look like? How could I rewrite this in a simpler way that's similar to that? Now, again, step 0 is to make a guess. And if my guess is convergence, then I'm going to set my function to be a sub n. And if my guess is divergence, I'm going to set my function to be d sub n, or b sub n. So, looking at this, I'm going to compare this. I'm going to think about my series as being similar to 6 to the n over 5 to the n. And you might be saying, okay, cool, but that's not anything we know. But if I then rewrite this, I can think of this as 6/5 to the n. Now all of a sudden this is looking like a series I know very well. This is looking like a geometric series with p equal to 6, I'm sorry, with r, not p, with r equal to 6/5, which is greater than 1, which makes it divergent. So step 0 is that I'm going to guess it's divergent, and therefore I'm going to let b sub n be 6 to the n plus n over 5 to the n minus 1, and a sub n be this geometric sequence. The summation, a sub n is just going to be 6/5 to the n. And I have to show that a sub n, 6/5 to the n, is less than or equal to 6 to the n plus n over 5 to the n minus 1. And again, it's not completely obvious from the beginning, so let's take a term-by-term comparison. If n is 1, my first value here is 6/5, whereas my first value on the other one is 6 to the first, which is 6, plus 1, so that's 7, and then 5 to the first, which is 5, minus 1, which is 4. So right off the bat, 6/5 and 7/4, this guy's bigger. Okay, let's look at one more just to be safe. So this would be 36/25, and this guy would be 36 plus 2, so 38, and then 25 minus 1, 24. This guy's bigger. So again, yes, that's true. Step 2 is to say, okay, well, because that's true and my guess is divergent, then I'm looking at this row that says the summation as n goes from 1 to infinity of 6/5 to the n is a divergent geometric series with the absolute value of r being 6/5, which is greater than 1. Therefore, I can say that the summation as n goes from 1 to infinity of 6 to the n plus n over 5 to the n minus 1 diverges by direct comparison to my divergent geometric series. See, I've been doing way too many p-series questions. My divergent geometric series, the summation as n goes from 1 to infinity of 6/5 to the nth. Coming up next, we're going to take a look at another comparison test, which is the limit comparison test.